Artificial intelligence has a kind of dirty secret. It's incredibly hungry for energy. Today, we're going to break down a new research paper that might have just found the answer, a way to build AI that's way smaller, smarter, and radically more efficient. Let's dive in. So here's our roadmap. First, we'll get into AI's massive energy problem. Then we'll explore a much more elegant solution, thinking in simple zeros and ones. We're going to uncover the three big hurdles that have been holding this whole idea back, and then reveal the absolutely brilliant three-part breakthrough that finally cracks the code. And you're going to want to stick around for the end, where we see just how much smaller, smarter, and faster this new AI really is.
All right, so let's kick things off with the problem that's driving all of this research. Why on earth is the AI we use today so demanding? The AI models that are running everything right now, from your favorite image generator to the latest chatbots, they're what we call floating point networks. The best way to think of them is like a gas-guzzling muscle car. Yeah, it's unbelievably powerful. It can do some amazing things, but man, does it burn through fuel. In this case, that fuel is computation, memory, and a whole lot of electricity. And this isn't just some abstract technical issue for data centers. As the researchers point out right here, this high cost has very real consequences. It's a huge burden on the environment, and it makes it incredibly difficult to get powerful AI running on the gadgets we use every single day. Like our phones, our watches, or our smart speakers.
So this massive energy problem has forced researchers to look for a completely different path forward, a much more elegant approach that gets back to the basic language of all computers. And this slide just lays out the two philosophies perfectly. On one side, you've got our gas-guzzling muscle car. That's a standard AI running on really complex decimal math. But on the other side, that's the goal. Boolean AI, the sleek electric vehicle. It works with simple binary logic, just zeros and ones, which makes it, by its very nature, incredibly efficient and compact. So what even is a Boolean network? Well, at its core, it's an AI that literally thinks like a computer chip. It doesn't need all those messy decimal points. It just uses simple logic gates, things like and, or, not, to process everything as a clean series of zeros and ones. It's AI built for efficiency from the ground up. But, and this is a huge but, here's the catch. The whole idea of using Boolean logic is amazing. In theory, making it actually work in the real world, that has been a massive headache for researchers. See, it's one thing to build a simple binary network, but it is a whole other ballgame to make one that is both super tiny and just as accurate as the big guys. And this brings us right to the heart of the story. If these Boolean networks are so great, what's been stopping them? Turns out it all comes down to three major roadblocks.
It's the big question, right? And the answer is that researchers have been stuck on three really specific and really tough challenges for years. Okay, hurdle number one. Inefficient connections. Imagine trying to build a brain, but the wiring is totally random and fixed in place. The paper calls it highly inefficient. Second, a bulky architecture. The old designs for tasks like recognizing images used these really clunky, complicated structures that just took up way too much space. And finally, the trickiest one of all, what they call the discretization gap. This is what happens when you train a model using all those flexible decimal numbers, but then at the last second, you force it to speak only in zeros and ones. That sudden switch usually caused a huge drop in performance.
Okay, so we've got our three big problems. But now for the really cool part. This new paper comes along and just brilliantly knocks down every single one of those hurdles with a three-part solution. This breakthrough really comes down to three key ideas. First, they figured out how to let the network literally learn its own best connections while it trains. Second, they completely reimagined the architecture for image tasks from the ground up. And third, they came up with this really clever way to train the network with its final binary destination in mind the entire time. So, let's look at that first innovation, the wiring. Instead of that fixed, random mess, the network can now basically rewire itself as it's learning, finding the absolute best connections on the fly. And here's the crucial part. It does this without needing any extra instructions or what researchers call parameters. This is huge because it avoids the massive memory costs that totally killed earlier attempts. Next up, they went after the bulky architecture. For vision tasks, they just tossed out those old, clunky, tree-like structures, and they replaced them with these tiny, super efficient building blocks. They're called kernels, that each perform just one single, simple logic operation. This move dramatically slimmed down the whole part of the network that actually sees and processes images. And that brings us to their brilliant fix for that discretization gap. So instead of making that jarring switch to binary all at once at the very end of training, they do it gradually. They essentially freeze the network layer by layer, turning it into a pure Boolean circuit, piece by piece. This forces the layers at the end of the line to learn how to work with the already binary information coming from the first layers. It completely closes that gap and keeps the accuracy high.
So, what happens when you put these three breakthroughs all together? Well, this is where we get to the real wow factor. And trust me, the results are pretty wild.
So what did all this work actually achieve? Well, it boils down to one number: 37 times. Just let that sink in for a second.
Now, here is the real kicker. It's not just 37 times more efficient. No, this new method uses up to 37 times fewer operations while getting better accuracy than the previous best model out there on a standard test. This isn't just a small step forward. It is a massive leap in both efficiency and performance. I mean, just look at this chart. It tells the whole story. That tall bar on the left, that's the number of operations the old method needed, 6.2 million. And that tiny little bar on the right, that's the new method, just 168,000. It's not even a fair fight. And this table here breaks it down even further. Look at this. Their new small model gets a higher accuracy score than the previous large model. And get this, it does it using 45 times fewer neurons and 37 times fewer operations. It's a win in every single category. It's doing so much more with so much less.
So, okay, 37x is a really cool number, but why does it matter to you and me? Well, it means we're closer than ever to having seriously powerful AI running right on our phones and watches without killing the battery in an hour. It means lower electricity bills for the giant data centers that power the internet. And for developers, it means AI is more accessible and can be used for faster, real-time applications that were just a pipe dream before. This is a real game changer.
And all of this leaves us with one last big question to think about. We've just seen a jump in efficiency that's almost hard to wrap your head around. So I'll just leave you with this. What brand new doors open up? What becomes possible when the AI that's shaping our world suddenly becomes 37 times more efficient? It's pretty exciting to think about. Thanks for joining me for this breakdown.